Good morning, good afternoon, good evening, ladies and gentlemen, and welcome to this talk at the DSP online conference on Kalman Filters. Hope you're all well, and I'd like to thank Stefan for the invitation to come and present today. We are, for the next 40-50 minutes, going to discuss linear Kalman filters. We will discuss the advantages, disadvantages, and in fact limitations, because I'm sure some of you will be familiar with Kalman filters to some extent, and will appreciate that in some applications, not the one I was involved with, nonlinear Kalman filters are much more appropriate. So I will discuss those briefly at the end, but we are going to focus on linear Kalman filters. Like a lot of my talks at the DSP online conference and other conferences, they really should be subtitled Standing on the Shoulder of Giants, and this one should really be. And I will refer you guys to those giants as I go through the talk. Okay, so Kalman filters. Before we get into those, for those that don't know me, I should just introduce myself. I am not the former US Senator who was really heading for a potential vice presidential position until he got caught in an extramarital affair. DSP is not that interesting or exciting. There will be nothing like that this afternoon, I'm sure. I am a DSP engineer with over 40 years experience now, and currently work as a DSP consultant and run a number of training courses for customers and companies. I am also the author of a digital signal processing and machine learning library called SigLib, and I've been a presenter at the University of Oxford for the last 36 years on their digital signal processing course. Okay, so that's a bit about me, enough. Let's get into Kalman filters. We're going to take a very much a top-down approach to filters, Kalman filters, through this module. We're going to discuss high level, then how to design them, look in deeper dive at two particular components within the Kalman filter, and we'll end with a demonstration at the end. Okay, so what does a Kalman filter do, and what are we trying to achieve? Well, let's consider a signal embedded in noise. If we have a transducer, for example, trying to detect the position or velocity of a moving object, how do we actually estimate the true signal state if that signal is embedded in a very large amount of noise? Well, we could use moving averages or filters, more accurate filter, more focused filters, but in general these approaches are slow to converge. So how can we design an algorithm that gives us a much faster convergence, particularly in a system where the signal is corrupted by stochastic or Gaussian noise? This is where the Kalman filter comes in. So before we look at the Kalman filter itself, let us just think about the estimation of the position of a moving object. If we wish to estimate the position of an object, and we have a previous measure for position, for example, and we know the velocity and acceleration, then using the kinematic equation shown here, we can easily estimate the current position from the starting position x0 plus the velocity over time. Let me just choose my pen. So with velocity and time and acceleration and time squared, we can use this equation. We all know this, I'm sure. Current position is the previous position plus the velocity times the time interval plus half the acceleration times the time interval squared. So using this, we can estimate the new position of our moving object. But in order to do that, we need to be able to measure position and velocity and other things accurately. And this is where the problem arises. Because in many applications, exact measurement of the current state is impossible. And in other applications, it's only possible with significant cost or effort. And this was true of the application I was involved with, where it was very expensive to measure the position of this object accurately. So the customer tried using cheaper transducers and Kalman filters to replicate the accuracy, and that's exactly what we did. Now, estimating the state, or whatever that state is, position and velocity of an object, can be difficult due to many different things. Obviously, measurement noise, sensors and so on, but also process noise. Is there an error in the process of trying to compute the state of that system? So how do Kalman filters help? Well, Kalman filters use state estimation to simplify the process. Kalman filters are a recursive algorithm, we'll see that. A recursive estimation of the current state based on the previous iteration and the current new measurements. So we use the previous state estimate and the current measurements to compute the new state estimate, position, velocity, whatever we're trying to compute. As I mentioned at the start, there are extensions for estimating nonlinear systems, but we're not going to cover those this afternoon my turn. Kalman filters basically use a state space model in the time domain for performing this estimation, and that's what we're going to talk about. So the basic major benefit of the Kalman filter is it's going to predict the next state while filtering out the noise or uncertainty in the system observations. Okay, excellent. So looking down a bit further, the Kalman filter is a dynamic model of the system being observed. So it's a mathematical model of the system, and it's widely used in navigation, tracking GPS applications, and control systems where there may be a high level of noise. It's a linear recursive algorithm, as we discussed, and it's optimal for linear with Gaussian or normally distributed noise. In fact, the Kalman filter provides an exact minimum mean squared error estimate of the state, and we'll talk about that in a few minutes. Essentially, the Kalman filter uses a time-varying linear filter for its mathematical representation, and state variables are related by first-order differential equations, so nothing high-order, nothing complex. But the Kalman filter can represent single input, single output, multiple input, multiple outputs. We might have simple system with just position, 1D position, or multiple inputs, multiple outputs, position, speed, in fact, multiple dimensions in space, 3D, etc. The Kalman filter itself is not a unique structure, but it's the method used to design the filter that makes the Kalman filter the Kalman filter. So let's go and have a look. Before we do that in detail, let's think about some key concepts. The first key concept is the state. What are we trying to estimate? Position, velocity of our particle, object, etc. The next concept is the process model. How does the state evolve over time? Obviously using Newton's equations if it's equations of motion, if it's a particle, an object moving. The measurement model. The measurement model is how sensors observe the state. GPS, transducer, whatever your transducer is, how is it observing the state, and what noise levels do we have, etc. Both models and measurements are uncertain, and that's the sort of key concept of the Kalman filter. We are assuming that both the model and the measurement of our position, whatever, of our state, are both noisy. So we have process noise, which is how the system evolves, and that's the noise in the system, and we have measurement noise, which is the sensor inaccuracy. Have we got a noisy sensor, basically? But now comes the key to the Kalman filter, and it's the Kalman gain. The Kalman gain is a time-varying parameter between 0 and 1, and the magnitude of the gain reflects the confidence the Kalman filter has in the current measurement, input measurement from our transducer sensors, versus the previous prediction. So depending on the value of the Kalman gain, we either give more weight to the prediction or more weight to the measurement. And the question is, how do we compute that? And the answer is we use the variance of the signal. What's variance is the noise within the signal. How much does the signal vary? If a signal has a high level of variance, it has a very high noise level. So the estimation of a single input sample, for example, from a noisy transducer, is going to be less accurate than from a very high quality sensor with very low noise level. So we use the noise level, the variance on the signals as a measure for how good they are for estimating the current state of the system. And it's the Kalman gain that makes that call ultimately. Okay, so here's the loop. We have our Kalman gain in the middle, and our two inputs to this computation are the prediction from the previous time round the loop and our measured input value. We use these combined with the Kalman gain to give us our new predicted value, which then goes back around the loop to be used again. And so the Kalman gain is continually updated, but depending on our new prediction and our new measured values. And in fact, there are two states to this loop that we'll see in a few minutes. The Kalman filter has two phases. The first phase is prediction, where we are going to predict the next state using the system model. And in parallel with that, we're going to predict the uncertainty in that state, the variance. And then the second stage is the correction stage, where we update the state estimates to allow us to go around the loop again. So here we take the new measurements, we compute the Kalman gain, we update the state estimates using the weights, and of course we update the uncertainty again for going around the loop. So the key to the Kalman filter is the Kalman gain, and the key to computing that is these two stages. Prediction, we're going to predict the next state and the uncertainty in that state, and then the correction, where we're going to compute the correction, compute the Kalman gain for the next time around the loop. Okay, so it's effectively a feedback system, and we can represent feedback systems shown using the equation in the top left of this slide. Excuse me a second, time for a cup of tea. And of course we have our feedback coefficient A and our feed-forward coefficient B, and very simple. If A and B are used as weighting values for estimating our output y of n based on our input x of n, we all know how a one-pole filter works. But we can take that concept and apply it to our Kalman filter. So if we look at the filter on the right, we basically have our two coefficients, B and A, where we have a time-varying gain on either the previous output estimate, this previous state, or the new input. So xn being the input, and then y hat of n being the state estimate. So by taking the input x of n, multiplying it by a time varying gain b, we can then combine that with our previous estimate y hat of n, previous estimate through our time delay. We then combine that with our multiplying factor a to put that into our predictor with our input value to get our new state estimate out of the system. So it's this constant feedback that is what we're going to see in the Kalman filter. And it's the relative weights of these two parameters, A and B, just shown in this simple one-pole filter type example, that are going to be how we control the Kalman filter performance. Okay, so let's go and look at the Kalman filter in slightly more detail. Okay, well, the first thing is, what state are we going to start our Kalman filter with? Well, we need to provide an original, like an initial estimate for, let's say, position, velocity, whatever we're trying to measure, and an initial estimate for the error in our estimate. So we've got the original estimate and then the error in our original estimate. We need to kind of think of what those values might be. So those are like the initialization values going into our algorithm. And they're important because once they go into our algorithm, then as the algorithm is processed and we go around this loop that we've talked about, those values are going to be updated each time around the loop and become more and more accurate. So how do they do that? Well, we start with our previous estimate original estimate coming in here. And now we take in a new data input value, the new measured value. We take both of those in to compute the current estimate. We then take that estimate and we compute the new error in the estimate. And then we pass these values back around the loop. So let me just clear the diagram slightly, because the current estimate now becomes the previous estimate. That's all it does. That is our state estimate. That's what we pass on down the line in our processing chain. But within the Kalman filter, we store the current estimate for the next time around the loop. And then we take our error in the estimate and we pass that around the loop back into our next iteration around the loop again. Okay, so that's the, if you like, the computing the current estimate. But we also need to compute the Kalman gain, which I've talked about as well. And in fact, what we do is we take this previous error value in the estimate, we take the error in the data measurement, and we use those values to compute the Kalman gain, which is then passed on here to then decide how we weight the measured or the previous estimate values. So we take the error signals, the variances, we compute the Kalman gain, and then we use the Kalman gain value to weight the estimate or the measured value. It's as simple as that. Now, before I move on, I just want to highlight one of the giants whose shoulders I'm standing on today, Michael Van Beezen. Done this amazing YouTube series. You can all go and Google it and find it. Without him, my life learning about Kalman filters many years ago would have been way harder than it was. If you are interested in this subject, I highly recommend you go and look at his tutorial series. There's like 50 odd videos. They're all only about 4 or 5 minutes each long, 10 minutes long maximum. Fantastic, really, really good. Okay, so that's the high level view. Before we go and look in a little bit, excuse me, let me just grab it. Before we go and look in a little bit more detail, I just want to cover a couple of more key points. The first is the state matrix. This is the matrix that is going to store our position and velocity. Now, if we just have a single particle, single object traveling with a position and velocity, it's very easy. We have this state matrix structure that looks like this. But what about if we have multiple dimensions, 3 dimensions, X, Y, and Z? Well, the best way to store the data that leads to the most efficient coding solution is to store the data like this, where we have all the positions, excuse me, followed by all of the velocities. It just leads to a neater solution. So Michael's video tutorial goes on in a little bit more detail about that. But stick with what Michael recommends. Stick with this format and you won't go wrong. Okay, so that's the state matrix. It contains position and velocity. But what about variance and covariance? Well, I've talked about variance in the earlier. So variance again is how large a signal varies from its mean value. So if the noise is very low, the signal varies. The variance is also very low. If the signal has very high noise level, then the variance is very high because there's a lot of variance from the mean level. The covariance quantifies the degree to which two completely separate variables change together. They may, or it tells how separate they are, if you like, how similar they are. So if variable x varies in one way and variable y, the variation of that almost exactly tracks the variation of x, then the covariance has a high value. If the variation of y is completely random compared to the variation of x, then the covariance is very, very low. So here we see the equation where we have each input sample in our array. We're going to sum, but we're going to sum the multiplications of the x and y values, but where the x and y values have their mean values removed. So it removes the mean, it just looks at the variance in each signal and multiplies those through, and through that we get this measure of the covariance of the two matrices. Okay, so those are the two key points. Let us now go on to look at the flow diagram of our Kalman filter. Again, special thanks to Michael. Now, I'm going to continue this top-down approach to this discussion. The two key parts to this algorithm are the prediction and the update correction states. So we're going to save those for the next couple of slides. So we're going to look at all the bits around that, and in order to do that we can quickly shoot on to the next slide where I have included a description for all of the matrices and vectors used in the Kalman filter. Now, these sizes of matrices and vectors assume that this is a 2D Kalman filter. What do I mean by that? It is a filter that tracks position and velocity, 2 degrees of freedom, as opposed to a Kalman filter in 3D space, for example. So it has two state variables, two degrees of freedom. Now, for those that code in C and assembly code, I've included the sizes of the vectors, matrices here, so you can easily go and declare them in your code. Actually, you don't need to. You can download the code. I'll show you where later. Obviously, if you're doing this in Python or MATLAB, you don't need to worry about those. But anyway, here's the description. Here's the flow diagram, and over here on the left, not surprisingly, we have our initial values for our state estimate. That's x, and our process covariance matrix. That's the estimation error in P. So those are the initial values. On boot up, we write those into the previous values, as you saw in the earlier diagram. That's it, they're done. We don't do that anymore. What we're going to do is go around this loop, and essentially we're going to update the estimate of our state variables and the error estimate for those values. So those values come out of here. Those values also go in here for the next time around the loop. So this first block here in the top left-hand corner is really just the block that stores the previous estimates for the previous time around the loop. So what's new? Well, what's new is over here on the right-hand side. This is our measurement input. This is the input from our sensor. We have three variables in here. We have the observation matrix, C. This is what we've observed. We have our state estimate. Here, we're going to multiply those two together. And then we have our noise, measurement noise value here. So these are the three inputs into this equation. So if the input is X, then the output, by sort of common standards is Y. So that's the measurement input equation for the Kalman filter. So if that is the case, then the input to the Kalman filter is actually our variable Y. This caused me a little bit of confusion when I first did this until I watched Michael's videos, and then it kind of all made sense, because this is our input equation for computing our inputs. From inputs C and X, we get our output Y. But our input to our Kalman filter is the variable Y, and our output is the updated state X. So just a little something to be careful of is all I'm saying. Okay, so that's it. So I say the only other equation we need to look at is this one here, where we're basically computing the process covariance matrix, or the estimation error. So we're just computing the error in our estimate, which we're going to save should it be needed further down the line in our process, but it will definitely be saved to go next time round the loop for the Kalman filter. Okay, so that's everything around the Kalman filter. What we are going to do now is to look at these two parts here. Deeper dive, the prediction stage and the correction stage. So first, excuse me, time for a cup of tea. Firstly, the prediction stage. We're going to update our estimate based on this little equation here, which has three components. The first component is we're going to take the prediction, the previous prediction, we're going to multiply that by this A, and this A is the state transition matrix, as per our one-pole filter that we sort of process we looked at before with the A's and B's. The A is not just a single value as it would be in a one-pole filter. It's a matrix. It's called the state transition matrix. So with that, we're taking the previous state and we're transitioning it using our known knowledge of how that changes. Equally, and that, remember, the state transition matrix incorporates position and velocity typically. So we're going to update both. Here we have the acceleration value updated by the acceleration matrix B. Now, for simple Kalman filters, we assume that the acceleration is constant, but of course it might not be. And then finally, we have our noise, process noise vector. So this is the noise in the system. So we take those components, we combine them together, and we get our updated state estimate. Having done that, we then need to compute the uncertainty or the error covariance matrix within that value, and we compute that using this equation here. So we take the process covariance matrix. So remember, covariance is the difference in how to, is the relationship between how two signals vary, one with respect to the other. So we take the process covariance matrix, how do the signals vary with respect to each other, and then we use those to update the new covariance matrix, the new noise. How much is the noise? And hopefully over time this uncertainty is going to reduce as the Kalman filter is going to start tracking the true state of our object. Okay, so that's the prediction stage. The correction or the measurement update stage is shown here. And the key equation is this one here. This is the equation that computes the Kalman gain. So, summarized it on the right here, we have this value R, which is the sensor noise in the flow diagram we saw earlier. If we look at this equation, if the sensor noise is small, then the denominator will be small in this equation, and hence K will be large, i.e. we will trust the measurement more than the previous prediction. So if the noise of the sensor is small, then we trust the measurement from the sensor. On the flip side, if the sensor noise is large, then we would trust the prediction more than the measurement. And of course the vice versa is also true. If we look at the prediction error, the estimation error, the process covariance matrix, PKP, if this value, the prediction uncertainty, is large, the numerator will be large, therefore K will be large, therefore we will trust the measurement more than the prediction. But equally, if P is small, the numerator is small, and we will trust the prediction more than the measurement. So you can see that as these two values of P and R vary, as if R was to get larger, the sensor noise is getting larger, the error on the measured value is getting larger, we would trust the prediction more, and vice versa. So that is basically how we compute the Kalman gain, which is then used to weight further on in the algorithm, weight either the prediction or the measurement. We then take our Kalman gain, put it into this equation here, and this is where we update the estimate with the weighted measurement. And then finally, we update the error covariance matrix to say how accurate is the signal. What is the error? What's the covariance on our of our signals? And as I mentioned, hopefully we will reduce the uncertainty in our measurement by an amount proportional to the Kalman gain. So hopefully our error estimate is always going to be moving down the slope. Okay, fantastic. Hope that's all clear. So, quick summary. We have to go round the loop once per sample. We predict the new state and its uncertainty. We take in the new measurement, which has its own uncertainty. We compute the optimal estimate when we overlap those two Gaussian PDFs, probability density functions. When they overlap the most strongly, then the output, the estimate, is most accurate, and hence the resulting uncertainty will be the smallest. So we keep going around the loop, we keep updating the prediction, and hopefully our estimate becomes more and more accurate all the way around the loop. Fantastic. Okay, so that's it. That's the whole algorithm. I'm going to provide you a quick demo, and this is very small, very simple Python script that shows you how this code works. It simulates a 1D Kalman filter, 1D in space, but with 2 degrees of freedom, position and velocity, with both noisy position and speed measurements. So basically what we're going to do is we're going to generate some signals that provide the true motion of the object, and we generate some noisy signals which we apply on top of those for position and velocity measurements, and then we're going to take those noisy signals, apply those to the Kalman filter, computing both hopefully the position and velocity states. We'll run it and then plot the results. Okay, so here's the Python code. Our usual imports, our simulation configuration parameters, sample period, total time, initial values for position, velocity, standard deviation, etc. And then our arrays, our state matrices for all of our variables, as per the table that I showed you on a previous slide. We generate our signals, simulate the true trajectory of the object using our kinematic equation that we looked at earlier, and then we come down here, we apply some random noise, and we're good to go. So we initialize our state estimates and our covariances. We're all good engineers, aren't we? So we always initialize our local variables to 0. We would never forget to do such a basic thing ever, of course. And then now we're getting into our Kalman filter. We start with our initial estimates, could be anything really, and for our state variables, position, velocity, and our covariance. And then we come into our Kalman filter loop. And actually, really, these last 2 lines here are just storing numbers in memory. So the key thing is these lines here, and you can see these exactly match, not surprisingly, the 2 main stages that I talked about earlier, the prediction and the update stages. And that's it. So we just compute our input prediction, our process covariance update. So we predict the new values, store those, that's it. They can be used later on in our algorithm, equation, whatever, plotting our position on a GPS map. And then we need to update the estimates and the noise and so on. And here are the few lines of code to do that. Again, exactly as per the flow diagram, nothing unusual there. And then finally, all we're doing is computing the mean squared error between our input values and our estimated values, and plotting some nice graphs. And sure enough, down here we have our graph for position. You can see the true position as a line, the measured position. You can see the magnitude of the noise compared to the magnitude of the signal. It's quite a high level of noise that I've applied here. And then you can see the Kalman filter estimate for the position. It becomes very accurate, actually very easy. And I suppose I could have added some code just to, I don't know, maybe do the same thing with a one-pole filter or a moving average filter, and I'm sure it would have taken a lot longer to have converged in time. So there's our position graph. Here's our velocity graph. Again, you can see convergence very quickly, even though we have a very high variance in standard deviation of our noise signal. And then here we have our error over time, and you can see how the errors reduce very, very quickly. Excellent. Okay, so that code will be up on the DSP Online page. It's probably up there already by the time you've watched this, so you'll be able to have a play with that. So moving on, I said I'd talk about some of the limitations. So what are the limitations of the pure Kalman filter, the linear Kalman filter? The noise must be Gaussian, otherwise you're not going to get a very good estimate of the covariance matrices. The system must be linear. I mentioned that earlier. So what happens, or what algorithms can you use if the real-world systems are nonlinear? Well, the following variants are very common. The extended Kalman filter, EKF, and the unscented Kalman filter, the UKF. What is the difference? The EKF basically linearizes the model that we've talked about using Taylor series expansions. The downside of that linearization process is that it requires the Jacobian matrix to be calculated, and that's computationally very expensive. There's another downside with the EKF, that in highly nonlinear systems, the state estimate can diverge. So it can lead to very poor state estimates in those kind of scenarios. So the most common solution to that is to use the unscented Kalman filter, which basically, rather than using linearization of the functions, the UKF uses a deterministic sampling technique, the unscented transform, to basically estimate the next stage by propagating these samples through the nonlinear function of the system. The EKF gives a much more robust solution than the UKF gives a much more robust solution than the EKF, so it is much more common to use that in GPS systems and so on and so forth. But unfortunately, it does require a higher computational effort to compute. It's like everything in DSP land. The more performance you require, the more MIPS you're going to need. Okay, so that's the Kalman filter. It's a very, very good algorithm, very efficient, very easy to implement algorithm for getting very accurate estimates of position, speed, etc. in a noisy scenario. It's recursive, so it doesn't need a lot of memory to store state variables, state arrays. Very efficient in terms of multiplications and so on. And it supports multiple estimation of multiple parameters, position, speed, etc. in multiple dimensions very, very easily. Very easy to expand the basic algorithm which I provided you with the code. If you want more code, C code, etc., feel free to go to my library, download it, and have a play. It's free for non-commercial applications, personal education, and so on. I've already mentioned one of the giants whose shoulders I'm standing on with this talk, Michael van Biezen. Here's a couple of the other references that I used when I was doing this work. So please go and check them out. And finally, thank you very much. I hope you enjoyed this talk. And enjoy the rest of the DSP online conference. Thank you to Jacob and Stefan for arranging it all. Appreciate it. Bye bye.